So there's many ways to define the number e. And the approach we'll take in this class is related to the function 1 plus x raised to the 1 over x. Now, this equation shows up many times in many applications. One easy way is to look at compounded interest. So if you were to, say, compound your interest maybe one time, then this ratio would be 1, so would x, and this would tell you how much money you would have after 1 year. So it would be, put $1 in. After 1 year compounding, x is 1, and so this would be 1 plus 1, 2, raised to the 1 power. You'd have all of $2. Now, if you compound more than once, then 1 over x is the number of times you're compounding. And so if I compound 100 times, I would be raising, this would be 1 over 100. And this right here would be 1 over 100. So we'd have 1 plus 1 over 100 raised to the 100th power. So really what happens when we compound a lot of times, the higher the number of times you compound, then this value x gets smaller, whereas this power obviously gets larger. And so if one were to compound forever, like an infinite process, then this exponent becomes an infinite value, and this value here becomes an infinitesimal. And so we'll investigate. So being infinitesimal means that x is getting smaller and smaller, getting closer and closer to 0. So let's investigate what happens when we get closer to 0. We're looking at what are the values of my output around here. Now we see it gets very steep, but the graph seems to stop there. Now, of course, you put in 0 into your function, and we'd be raising to the 1 over 0, which is not defined. So we can see that we're undefined there. But nonetheless, close to it, we can have values, zoomed way out here, it looks like about 2.577. So here we're going to zoom in. And now we've zoomed in quite a bit. We can see on our x scale, we are ranging between 0 and 0.5. And our values for y, as we march in, seem to be pretty stable. 2.15, 2.16, 2.17, 2.18. So it looks almost flat when we're zoomed this far in. We can zoom in even further. And now you can see our x scale is going from 0 to 5 times 10 to the negative 9, right? This is 5.00090 zeros up to the 5. And so again, if we look at our values for y, there's absolutely no change. Now, if my scale were to go further out, we're only going to 3 decimal places, it would change, but it's super flat when we're at this zoomed in level, almost to the infinitesimal level. And so this tells us that if we were able to, if we had an infinitesimal grapher, we could zoom in and we should be infinitesimally close to some number. Well, what number is that? It's tempting to call it 2.718, but in fact, through some deeper mathematics, it is no rational number, and we call that number e. So in that graph, we were investigating the values of 1 plus x raised to the 1 over x for small values of x. And we saw that it got close to some number, 2.718, and then, as I suggested, that keeps going. So we're mathematicians. We can define things. It seems reasonable that this should be then defined if I let x be not just a small real number, but actually let it be an infinitesimal. And so if we look at the standard part of 1 plus 1 over, 1 plus epsilon raised to the 1 over epsilon. Right, so I'm going to put an infinitesimal in for x, where epsilon is an infinitesimal. Then it seems reasonable that there should be a real number that's infinitely close to this, and we will call that number e for the natural number, or the Euler number. That's what e is. It's called the natural number or the Euler number. And for our purposes, we will define it as being the standard part of 1 plus epsilon raised to the 1 over epsilon, where epsilon is an infinitesimal. Right? So this is our definition. Now that we have this definition, we can go about and define what the derivative is of the log base e of x. So if y equals log base e of x, this means that e to the y is equal to x. And this logarithm comes up so often in application, so often in mathematics, that we get lazy and don't want to keep writing all these letters, and so we write the natural log ln of x. But ln of x is just log base e of x. So our question here is, what is the derivative? What is the derivative of the natural log with respect to x? And we will build our proof of what this should be directly from the definition. So we know that the differential of the natural log of x, so the differential of the natural log of x with respect to x has got to be the standard part of natural log of x plus delta x minus the natural log of x divided by delta x. I'm hoping by now that you have this definition memorized. This is not a surprise to you. And now we're going to do some simplification based on our log rules. Right? We've got the difference of two logs. So this is equal to the standard part of 1 over delta x times the natural log of x plus delta x, all divided by x. Right? Remember our quotient rule for logs says that if I've got a quotient on the inside, that's the same of natural log of x plus delta x minus the denominator. That's what we have here. So that simplifies to that. And then we also have our rule that constants in the front of our logs come in and become our exponent. So I can bring that in, and I'm going to do a little simplification here. And so this is equal to the standard part of the natural log of 1 plus delta x over x, all raised to the 1 over delta x. And so now we've kind of crunched this together, created one expression here. However, we still can't evaluate the standard part, because if I did, I'd come through and this is an infinite number. And so we need to get a little bit of a handle on that. What is that number? And we do a substitution here to make the math easy. Because the hardest part that I see in this problem is that if I could take care of this expression here, if I could get the x out somehow, I could work with this. Well, delta x is an infinitesimal, right? Delta x is an infinitesimal. That means that, and x is a real number. So that means delta x over x is some infinitesimal. Well, if it's an infinitesimal, that means there's some value epsilon, say, that equals delta x over x. So no, that's true. And then we're going to want to replace this expression here. And so solving for that, I get that 1 over delta x is the same as 1 over epsilon times x. Okay, so I'm going to make this substitution, putting those values in. So this is equal to the standard part of the natural log of 1 plus epsilon, all raised to the 1 over epsilon times x. And what's really great here, you may not see it right off the bat, that's an x. You may not see it right off the bat, but this expression here, 1 over epsilon plus x, let me rewrite it in a way. And so I'm going to erase this and rewrite it, because fractions, this is just multiplication in the denominator, so this I can rewrite. I'm not changing it, I didn't make a mistake, but I'm just going to rewrite it so that we can see something more clearly. This is 1 over epsilon times 1 over x. Now, why did I do that? Why is that nice? Well, this whole expression is being raised to the 1 over x power now. If it's being raised to the 1 over x power, that means this can come out as my coefficient. And in fact, it's a real number, so even better, it can come all the way out of my standard part. So now, simplifying and doing those two steps together, I get that this is equal to 1 over x. So it's equal to 1 over x. Because remember, this came out of the natural log function, and then I can simultaneously factor it out of the standard part. So this is 1 over x times the standard part of the natural log of 1 plus epsilon, all raised to the 1 over epsilon. All my brackets. Okay, so the x came out, and I'm taking the standard part of the natural log of 1 plus epsilon raised to the 1 over epsilon. And standard part, it can move through the natural log function. So this is equal to 1 over x times the natural log of the standard part of 1 plus epsilon raised to the 1 over epsilon. All right, so now I need to know what is the standard part of 1 plus epsilon raised to the 1 over epsilon. But that's exactly, let's scroll up, what we defined E to be. E is the standard part, our Euler number or our natural number, is the real number that's infinitely close to 1 plus epsilon raised to the 1 over epsilon. It is the standard part of that, which means coming down here, this is equal to 1 over x natural log of E, and E to what power equals E? Well, this is 1. The natural log of e is 1. And so this is 1 over x. Okay, a lot of stuff just happened, so let me recap. We've got that the derivative of the natural log of x with respect to x is 1 over x. There, we did the hard work, and now we never have to do it again. And in fact, we can use this to derive what the derivative of any logarithm, regardless of its base.